Okay, Unit 2, Bonding. 4.1, Ionic Bonding. Ionic bonds, an electrostatic attraction between oppositely charged ions. Something has an opposite charge, they are attracted to one another. Opposites attract, like charges repel. This is one of the fundamental forces of nature. It's just the way our universe works. General rule, a compound is ionic if it contains a metal and a nonmetal. So examples, sodium chloride, calcium phosphate, magnesium sulfate, potassium sulfide, silver phosphide. Now, it's a metal and a nonmetal, but you can see there's some polyatomic ions which are made up of nothing but nonmetals. So the easiest way really to identify an ionic compound is simply look at the compound. Does it contain a metal? So sodium chloride, so sodium's a metal, potassium's a metal, magnesium's a metal, calcium's a metal, silver's a metal, so it's an ionic compound. Now the metals by themselves are not compounds. And the bulk of this unit will be over covalent bonds, and those are nonmetals that are covalently bonded. Now remember, atoms tend to lose, gain, or share electrons to have the configuration of a noble gas. And so in the case of an ionic compound, the metals lose electrons to become positively charged, and chlorine gains electrons to be negatively charged, hence the attraction between the two, the electrostatic attraction between oppositely charged ions. An ionic bond forms as a result of electron transfer. So it's a nice little animation of that. Sodium chloride.
When sodium and chlorine react, the sodium transfers an electron to the chlorine, forming oppositely charged ions. Although the compound has no net charge, its component ions of opposite charge attract each other to form ionic bonds. In turn, these ions are attracted to others, and an ionic solid called a crystal lattice is created.
Now, sodium chloride is one of the best examples of an ionic compound, and IB is all over sodium chloride, so that's like kind of your go-to for an ionic compound. Electron dot structures can be used to show the formation of ionic bonds. And so sodium, remember, has one valence electron, so we can use one dot to represent that. Chlorine has 7 valence electrons. Remember the octet rule. So if sodium loses an electron, it'll have the configuration of neon, a noble gas. If chlorine gains an electron, it'll have the configuration of argon, a noble gas. So electrons transfer, and this results in the sodium ion and the chloride ion. Now, the way that we write this is we only look at the valence electron. So sodium has lost its only valence electron, so there's no longer any dots. And we put it in brackets and indicate the charge. And then for chlorine, gained an electron, and so it's now negatively charged, and it has completed its octet. A lot more on dot structures when we get to covalent compounds. Remember Lewis structures? They're coming. Ionic crystal lattice, a three-dimensional structure composed of regularly repeating positive and negative ions. So positive and negative. Now notice the chlorine is a little bit bigger, sodium is smaller. So when they're nestled together in an ionic compound, each of the ions getting as close to one another as possible, it forms an ionic crystal lattice. An ionic bond is the sum of all attractive and repulsive forces found within the lattice. So we have the attraction between, so let's look at this chlorine ion here. It has a sodium on all sides here that it's attracted to, but it's also being repelled by the other chlorine ions. So you have that attraction and repulsive force that's taking place. For an ionic compound to form a crystal lattice, you would have to have the attractive forces override the repulsive forces, which would always be the case for an ionic compound, or the ionic compound wouldn't exist. Okay. Now, when we talk about an ionic compound, a crystal lattice, We really need to understand how fantastically gorgeous these crystals are. So I pulled this off of YouTube, so enjoy. This is the formation of crystals. So imagine you have a glass of water with an ionic compound dissolved in it, and the water is evaporating away. When the water's almost gone, the ions will reform the crystal lattice. Depending upon the particular ionic compound, they'll have various shapes and various colors. Pretty cool, huh? All these shapes grow from the molecular level into the macroscopic world where we can see it. Again, all these shapes are completely dependent upon the size of the ions and the charges of the ions. Okay, we'll move on now. Goodbye, crystals. For sodium chloride, each chloride ion is surrounded by 6 sodium ions, and each sodium ion is surrounded by 6 chloride ions. This is referred to as a 6-6 coordination. So what we're saying here is, and this is a nice top view here. So let's look at this sodium ion here. So let's say that that sodium ion is that sodium ion there. You can see that you have a chloride on each side here, but this is looking at it in 2 dimensions. So it looks like you have 4 around the sodium, which is what we have here. So we have chlorine, 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 chlorine. But we also have a chlorine right above it and a chlorine right below it. And so that's going to be the case for all sodium ions and all chloride ions. Each one will be surrounded by 6 of its counterpart. Each sodium surrounded by 6 chlorides, each chloride surrounded by 6 sodiums. And again, IB loves sodium chloride, so that's the kind of question that you need to be able to be prepared to answer. Now, there's thousands of common ionic compounds, but just know sodium chloride is that 6-6 coordination. And if you've never looked at table salt under a magnifying glass, or microscope would be better, they look like little dice. They're cubic. And if you were to take a hammer and smash it, it would form smaller cubes. So this cubic shape here is what you would actually see. Naming ionic compounds. So you had a lot of this last year, so hopefully this will come back to you. We're not going to hit it nearly as hard, but you are responsible for it. Common monatomic ions. Monatomic means there's just one atom that has gained or lost an electron. So group 1 will lose 1 electron. Group 2 will lose 2. Group 13 will lose 3. Group 15, and now we're just talking about the non-metals. As you go down the families 15, 16, you'll find that you go from non-metals to semi-metals to metals. And so we can't say across the family like the other ones we just looked at. So just the non-metals in group 15 will have a -3 charge, and the non-metals from group 16 will have a -2 charge. So what's going on here is the octet rule. Group 1, 2, 13 are losing their valence electrons to have the configuration of a noble gas. And for 15, 16, 17, they're gaining electrons to have the configuration of a noble gas. So the group 15 is just 3 electrons away from a noble gas. 16 is just 2 away. The halogens are just 1 away. And of course, group 18 are the noble gases, and they won't have a charge. So you should be able to look just at the periodic table and know what the charge is for these groups. Polyatomic ions you should know. And so all of these, probably once upon a time last year, you could name. So if you haven't already, why don't you pause the video and see if you can name them. Of course, you have them on the back of your periodic table, but see if you can do it without looking. And I'll go over it in 3, 2, 1, and the answers are. Okay, so all of these, there's many, many polyatomic ions, but these are the ones specifically IB has earmarked for you to know. So you need to know these. And if you were to take the IB exam, you're not given that periodic table with the ions on the back. You would need to know these. Again, if you're taking the IB exam, I'll be talking to you about all that kind of stuff. Now, the names here are all the common names. There's a couple of additional names that are often used. So hydrogen carbonate, which is the name that IB prefers, is better known as bicarbonate. And you learned these, and this is both of these are just different ways of writing the same formula as acetate, but ethanoate is the preferred name. When we get to our last unit on organic chemistry, that'll make more sense to you. And the reason that it's written in the first way here, and this is the way IB prefers it, is it gives us a better sense of how it's bonded together. When we get to covalent bonds later in the unit, I'll address that and kind of show you how that works out. This is the compact way that you more likely learned it. It's exactly the same charge, same number of atoms, just written in a different way. Many transition metals can form ions with more than one charge, such as iron. Iron can have a positive 2 or a positive 3. Copper can have a positive 1 or a positive 2. Chromium can have a positive 2 or a positive 3. Okay. These different charges is what's called the oxidation state of that element. When we get to our unit on oxidation reduction, this will make a lot more sense to you. But we refer to these as different oxidation states, and you're absolutely fine just referring to it as a different charge. I just wanted to introduce that term now. Roman numerals are used to name transition metals, which is called the stock naming system. So, for example, if we were to name this compound of iron and oxygen, what we would need to remember is that oxygen always has a -2 charge. So we can determine what charge the transition metal, in this case iron, would have by just looking at the chemical formula. Since you just have one iron for the one oxygen, which is -2 charged, then that must mean that this is the iron with a +2 charge, or +2 oxidation state. So to name it, we use Roman numerals. So this would be iron 2 oxide. Now, when you write this, the Roman numerals are in parentheses, and there's no space between the name and the parentheses. And we use Roman numerals. The other possibility for iron is it could have a +3 charge, which is the case here. So we have 3 oxygens, so 3 oxygens, -2 would give us a -6. So the irons, since there's 2 of them, must be the +3. And so this would be iron 3 oxide. And this is the more common one. You would know this as rust, iron 3 oxide. Rules for writing ionic compounds. And they're very simple. We always write the cation first, whichever has the positive charge, and then combine the ions, like we just saw, so that the net charge is 0. So let's look at a couple of practice here. So we have sodium, the +1, and sulfide with a -2. So when we combine them together, we need to have the charges cancel each other out. So a simple little addition that you can do is we're adding together the charges. We want them to equal 0. So the only question is, well, how many do we need of each to equal 0? What are the coefficients? Well, if we have 2 sodiums and 1 sulfide, we would get this equation to work. So 2 sodiums give us a +2, 1 sulfide, -2 equals 0. So that tells us what the chemical formula would be. We need 2 sodiums. We use a subscript in the formula, of course, and 1 sulfide. Sodium sulfide. So we've got aluminum with a +3, sulfate with a -2. So we do exactly the same thing. We want to add together the charges so that it equals 0. So our coefficients would be a 2 and a 3. 2 times a +3 is a +6. 3 times a negative 2 is a negative 6. So combined together to give us a net charge of 0. So when we write our chemical formula, we're going to need to have 2 aluminums and 3 sulfates. We use parentheses when we have a polyatomic ion. You can see how confusing it would be if you didn't have a parentheses here. It would almost look like it's 43. So make sure you only use parentheses for polyatomic ions, ions that are made up of more than one element. Over here, you would not put anything in parentheses. That does not add to the information. So sometimes kids go crazy with parentheses. But please remember, it's only when you have a polyatomic ion. And the name of this is simply aluminum sulfate. Okay, practice. Name the following ionic compounds. So again, give you a chance to do this yourself. I will pause, or you can pause the video and try it. I will answer the questions in 3, 2, 1. Magnesium oxide, ammonium nitrate, copper 1 sulfate, chromium 3 hydroxide, iron 2 carbonate, and potassium hydrogen carbonate, or potassium bicarbonate. Now, some of these are a little bit of a detective story. The sulfate is a negative 2, so the copper, since there's 2 of them, must mean that the copper has a positive 1 charge. So that's why it's copper 1 sulfate. For chromium 3 hydroxide is a negative 1 charge. So since you have 3 of them, the chromium must have a positive 3 charge or oxidation state. So chromium 3 hydroxide. Now let me point out to you that this ammonium nitrate is an exception to the what we mentioned earlier, is that you always have to have a metal in an ionic compound. Ammonium is an exception to that. Ammonium is a polyatomic ion that has a positive charge. So this is an ionic compound, even though it doesn't have a metal in it. So it's an exception. It's the only one you're going to see. Properties of ionic compounds. They're hard and brittle, high melting points, and they're an electrolyte, which means that it conducts electricity when molten, or in other words, you heat it up to the point where it starts to melt, or you dissolve it in water. For example, sodium chloride, table salt, has a very high melting point, just 801 degrees Celsius, so eight times as hot as boiling water. It'll begin to melt. When that occurs, it will be able to conduct electricity, but you can just dissolve it in water and it conducts electricity. Now, exactly how it conducts electricity is something we'll touch on when we get to our unit on oxidation and reduction. I'm going to show you a little video here. You might want to take notes on a couple of things.
Properties of ionic compounds. Let us look at some ionic compound properties. Physical nature. Ionic compounds are hard solids, as the force of attraction between the positive and negative ions is very strong. These compounds are brittle and break when pressure is applied. Melting and boiling points. Ionic compounds have high melting and boiling points because of a considerable amount of energy that is required to break this strong inter-ionic attraction. Solubility. Ionic compounds are soluble in water and insoluble in solvents such as kerosene, petrol, and so on. Conduction of electricity. Ionic compounds, when in solid state, do not conduct electricity, as the movement of ions is not possible because of the rigid structure. But when ionic compounds are in a molten state, it is possible to conduct electricity, as the electrostatic forces of attraction between the oppositely charged ions are overcome due to the heat. This leads to ions to move freely and conduct electricity.
The one thing I'll correct him, most ionic compounds dissolve in water, not all of them. You might remember the solubility table where you determine whether a double replacement reaction takes place, but don't worry about that. This is just a pretty cool, called cleavage.
Crystals of ionic solids can be cleaved along well-defined planes. Potassium bromide crystals cleave along perpendicular planes. The shape of the crystal, and therefore the angles of the crystal's planes, depend on the submicroscopic arrangements of ions within the crystal lattice.
Isn't that cool? It was like that. The strength of ionic bonds are directly proportional to the charge of the ions and inversely proportional to the size of the ions. Note, the stronger the bonds, the higher the melting point. So when we talk about the strength of ionic bonds, well, that's directly related to the melting point and boiling point. The stronger the bond, the higher the melting and boiling point. Okay, practice. Circle a compound that would have the higher melting point or boiling point. Okay, so we have two pairs to compare. So first look at lithium fluoride and lithium bromide. Okay, now this will help if you remember the size of the ion so you can determine by location on the periodic table. So both lithium, both of them have lithium. So lithium is going to not be a factor. The only thing that will change will be whether fluoride is a stronger bond with lithium or bromide. So fluoride is above bromide on the periodic. Fluorine is above bromine on the periodic table. So, and they both have a -1 charge. So fluoride is going to be smaller than bromide. And so the lithium fluoride will have a stronger bond because it's a smaller ion. So lithium fluoride. For potassium chloride and calcium chloride. So chloride is the same on both. Now, even though you have two chlorides, that's not going to be a factor here. So don't let the number of atoms affect your answer. So when we look at these, so we have the potassium ion and the chloride ion, and then the calcium ion. Well, potassium and calcium are in the same period. So potassium is the first element, calcium is the second element in period 4. So calcium is going to be smaller, but it's also going to have a +2 charge. So it's both smaller and has a greater charge. So that is going to be a greater attraction. So it's the calcium chloride. That is the end of the notes.